ship is 10 kilometers due south of a lighthouse at noon. So here's the ship, here's the lighthouse. The ship is travelling at 50 kilometers per hour on a bearing of theta, as shown below, where theta equals inverse tan of 4 over 3. On the diagram above, draw a set of coordinate axes that take the lighthouse as the origin, the line east-west through the lighthouse as the x-axis, and kilometers as units. So here's east-west, or west-east. It's our x-axis. Here's the origin, where the lighthouse is. It is coordinate 0, 0. The ship is 10 kilometers south of the lighthouse. Theta is an angle such that theta is inverse tan of 4 over 3. So if we can show theta as part of a right angled triangle, then the tan of theta is 4 over 3. The tan of theta is opposite over adjacent. So we could get the sine and cos of theta by completing this right angled triangle. The hypotenuse of this triangle is 5. We just get that from Pythagoras. So we can see that the sine of theta is opposite over hypotenuse. The cos of theta is adjacent over hypotenuse. And of course the tan of theta is 4 over 3, opposite over adjacent. This point here has coordinates 0, minus 10, because it's a point that's below the origin. So its y value is negative. Now, this arrow here represents the velocity of the ship. So this arrow, also known as a vector, has a certain magnitude and direction. Its magnitude is 15. The magnitude is the speed of the ship. So this is the speed. When we combine the magnitude or speed with direction, we have velocity. So the velocity is this vector here. Now, the ship is going to move along this line here, so I've extended this line on to show the path of the ship. To get this equation of this line, we need one point on the line, which we have, 0, minus 10, and we need the slope of the line. So how do we get the slope? To get the slope of a line, we need to get this angle in here. I'll call this angle A. This is the angle measured anti-clockwise from the positive x-axis to the line. It's a fact that the slope of a line is the tan of that angle. The reason why is because the tan is opposite over adjacent, or rise over run. In other words, y2 minus y1 over x2 minus x1. So that's important. So the slope of any line is the tan of the angle that that line makes, measured anti-clockwise from the positive x-axis. So in this case we will have a positive slope, because A is an acute angle. It's an angle that's between 0 and 90. The tan of such an angle is positive. If our line was going in this direction like this, our angle would look like this, and the tan of A would be negative. The tan of A would be less than 0. So we would find that A is a negative angle. Sorry, the slope is negative. Tan of A is the slope. How do we get the slope of this line? How do we get the tan of A? Well, this is angle A, so is this angle here. But notice that theta and A add up to 90 degrees. So we could refer to this triangle here. Theta plus this angle up here add up to 90 degrees as well. These two angles add up to 90. So we can see that from this triangle, the tan of A is the side opposite A, which is 3, divided by the side adjacent to A, which is 4. So the tan of A is actually got by taking the tan of theta and turning it upside down. 4 over 3 becomes 3 over 4. So we can just look at this triangle here. So that's the slope, and now we can get the equation. The equation of a line is y minus y1 equals m times x minus x1. So y1 is minus 10, y minus minus 10, or y plus 10 equals the slope 3/4 times x minus x1, which is 0. Multiplying both sides by 4, we get 4y plus 40 equals 3x, or 4y minus 3x plus 40 equals 0. Part C. Find the shortest distance between the ship and the lighthouse during the journey. There are two ways we can do this question. The shortest distance is the perpendicular distance of the lighthouse to the path of the ship. So I'm going to do it in two ways. the first way I'm going to do it is to look at this right angle triangle here. We're interested in this distance, which I'll call D. What I want to do is bring in the side we're looking for, which is D, and the side of this right angle triangle that we have, which is 10. D is the side opposite theta, 10 is the hypotenuse. So it's sine of theta that brings in both of those. Sine of theta is D, which is the side opposite theta, divided by the hypotenuse, which is 10. So that means that D equals 10 times sine of theta. Now what is sine of theta? Well, we had that earlier. Sine of theta is 4/5. So we get 2 times 4 is 8. D is 8 kilometers. Now that's by far the easiest way to do it, I suppose. The other way to do it would be to get the perpendicular distance of the point 0, 0 to this line here. So the perpendicular distance formula involves writing our line in the form AX plus BY plus C equals 0. So I've actually just changed the signs, but you don't have to change them. I've written our x term first, then the y term, then the constant term. A is the coefficient of x, B is the coefficient of y, C is the constant term. The distance is given by ax1 plus by1 plus c divided by the square root of a squared plus b squared. A, B and C are these values here. And x1, y1 is the point we're interested in getting the distance of the line from, which is 0, 0. 0, 0 is x1, y1. So we have 3 times 0 plus b, which is minus 4 times y1, which is 0, plus c, which is minus 40. That's divided by the square root of a squared plus b squared. 3 squared plus 4 squared. We want the absolute value of this. That just means that you make it positive. So we see we have 3 times 0, 0, 4 times 0, so we get minus 40 divided by the square root of 3 squared plus 4 squared. Well, that's root 9 plus 16, root 25, which is 5. So 40 divided by 5 is 8, so 8 is the answer. That's what we had up here. In the next question, we want to find the time at which the ship is closest to the lighthouse. So what we need to do is, first of all, get this distance here. So that's the distance the ship must travel in order to be closest to the lighthouse. The closest distance to the lighthouse is 8 kilometers. So we look at this right angle triangle here, and we just use Pythagoras Theorem. So if I call this distance x, we see that 10 squared equals 8 squared plus x squared. So I calculate x to be the square root of 100 minus 64. That's the square root of 36, which is 6. So this distance here is 6 kilometers. And what we want to do is find the time taken for the ship to cover a distance of 6 kilometers. Well, we just use the fact that speed is distance traveled divided by the time taken. That's if the ship is going at constant speed. If we're talking about average speed, well, if we get the distance traveled divided by the time taken, we get the average speed. But if the ship is going at constant speed, this will give us the exact speed of the ship, which we know is 15 kilometers per hour. So the distance, which is 6, divided by the time, which I'll call t, must equal the speed, which is 15. So we just interchange these. T equals 6 divided by 15. So we get an answer of 0.4 hours. The units make sense here because we have 6 hours, or sorry, we have 6 kilometers divided by 15 kilometers per hour. So the km's will actually cancel out. So we have 15 over h in the denominator. So if I multiply above and below by h, I cancel these h's here. So we end up with 6 over 15 hours. Hours are the units. Now, we were told that the ship is 10 kilometers due south of the lighthouse at noon. So at noon, which is 12 a.m., the ship was here. And 0.4 hours later, the ship is here. So 0.4 hours in minutes is 0.4 multiplied by 60. That's 24 minutes. So at 12 a.m. the ship is here, which means that at 12:24 the ship is here. So that's the answer. 12:24 a.m. or p.m. actually, sorry. Visibility is limited to 9 kilometers. For how many minutes in total is the ship visible from the lighthouse? Since the minimum distance of the lighthouse to the path of the ship is 8 kilometers, that's this distance here, then a distance of 9 kilometers would look like this. So when the ship is more than 9 kilometers from the lighthouse, the ship is not visible. But when the ship is less than or equal to 9 kilometers, in other words, when the ship is along here, is along this part of its path, then the ship is visible from the lighthouse. Because when the ship is anywhere along here, its distance to the lighthouse is less than or equal to 9. It's equal to 9 at this point and this point. It's less than 9 for any points between. So what you see here is an isosceles triangle. These two sides are the same. They're both 9. And we also have a line from the lighthouse that's perpendicular to the base of our isosceles triangle. That's the distance of 8 that we calculated earlier, this distance here. Now it's a fact that a line drawn perpendicular from this point down to the base of an isosceles triangle will bisect the base of the isosceles triangle, so that this distance here will equal this distance here. So we can see D is 8. I'll just write 8 in here just to make it clear. If we look at this right angle triangle, just this one here, we can use Pythagoras to find out what this distance here is. So we see that 9 squared, 9 is the hypotenuse, will equal 8 squared plus this distance here. I'll call it x plus x squared. So we have x equals the square root of 9 squared is 81 minus 8 squared is 64. So x is root 17, but the total distance is the distance from here to here is 2 times x. That's 2 times root 17. Now we know that for something going with constant speed, its speed is given by the distance traveled divided by the time taken. So the ship is going at a constant speed of 15 kilometers per hour. And that must equal the distance. We're saying this distance here from when the ship is visible from the lighthouse is 2 root 17 divided by the time taken, t. So to find out what t is, we just rearrange this, which is basically just interchanging these two. T is 2 root 17 divided by 15. So we get an answer of 0.497 hours. The reason it's in hours is that the distance is in kilometers and the speed is in kilometers per hour. So just like before, these cancel out and the h goes up. Now we need to convert this to minutes, so we just multiply it by 60.